Hello student, I am going to talk to you about infrared spectroscopy. It is also a kind of absorption spectroscopy. It is based on the fact that molecules have different kinds of energy levels and therefore absorb radiation in several regions of the electromagnetic radiations. When a molecule absorbs light of a given frequency, specific molecular effects occur depending on the wavelength absorbed. Low energy radio waves, for example, cause nuclear spin flip transitions, whereas more energetic UV radiation results in electrons being promoted to higher energy levels. Due to low energy level in IR, only vibrational excitation of covalently bonded atoms and groups occur. This is the electromagnetic radiation where you see infrared region, which is starting from nearly 33 per centimeter to 12,820 per centimeter. And this region is also subdivided into three regions. These are far infrared, mid infrared, and near infrared. And these are the properties of these regions. In near IR, the energy is in kilojoule per mole, that is 150 to 50. Wave number per centimeter, that is 12,800 to 4,000, and wavelength in micrometer 0.78 to 2.5. In mid IR, that is energy 50 to 2.5, wave number 4,000 to 200, and wavelength 2.5 to 50. Far IR, energy 2.5 to 0.1, and wave number 200 to 10, and wavelength again 50 to 1000 micrometer. And the portion of the infrared region most useful for analysis of organic compound is 4,000 to 600 per centimeter. Photon energies associated with this part of the infrared are not large enough to excite electrons, but may induce vibrational excitation of covalently bonded atoms and groups. In addition to rotation of groups about single bonds, molecules experience a wide variety of vibrational motions, characteristics of their component atom. Consequently, organic compounds will absorb infrared radiation that corresponds in energy to these vibrations, and absorption in this region implies the occurrence of vibrational transitions in the molecule while it remains in its ground state. Here is the representation of instrumentation. When a chemical sample is exposed to the action of higher light, it can absorb some frequencies and transmit the rest. Some of the light can also be reflected back to the source. And this is the representation. From all the frequency it receives, the chemical sample can absorb or retain specific frequencies and allow the rest to pass through it, that is transmitted light. And the detector detects the transmitted frequencies, and by doing so also reveal the value of the absorbed frequencies. For a molecule to show infrared absorption, it must possess a specific features, that is selection rules. That is, an electric dipole moment of the molecule must change during the vibration. These are heteronuclear diatomic molecule, for example HCl, HBr, etc. And the dipole moment of such a molecule changes as the bond expand and contract. These are called IR active molecules. In the alternating electric field of the radiation, remember that electromagnetic radiation consists of an oscillating electric field and an oscillating magnetic field perpendicular to each other, interact with fluctuation in the dipole moment of the molecule. And if the frequency of the radiation matches the vibrational frequencies of the molecule, then radiation will be absorbed, causing a change in the amplitude of molecular vibration. IR inactive molecule is a homonuclear diatomic molecule because its dipole moment remains zero no matter how long the bond. For example, O2, Cr2, Cl2, Br2, etc. And it is not necessary for polyatomic molecule to possess permanent dipole moment in order exhibit IR absorption, provided that some polar bonds are present in the molecule. For example, CO2 molecule, which we discuss later on. And here is the molecular vibration. The two atoms joined together by a chemical bond, maybe single, double, or triple bond, macroscopically can be composed as two balls joined by a spring. The application of a force like stretching of one or both the ball atom may from each other or closer to each other, bending of one of the atom either vertically or horizontally, and then release of the force result in the vibration on the two ball atoms. And these vibrations depend on the strength of the spring and also the mode, stretching or bending, in which the force is being applied. And for a diatomic molecule, only one vibration that correspond to the stretching and compression of the bond is possible, and this account for 1 degree of vibrational freedom. Here is the representation of vibrational mode leading to IR absorption. And extreme left, these are in top symmetric stretching vibration. Both outside atom move away from or towards the center. And next one is asymmetric stretching vibration. As one atom moves towards the center, the other moves away. And rest four are bending. Symmetric bending vibration in a plane, that is called scissoring. Asymmetric bending vibration in a plane, that is called rocking. And symmetric bending vibration out of a plane, that is called twisting. And asymmetric bending vibration out of a plane, that is called wagging. Polyatomic molecule containing many N atom will have 3n degree of freedom. Looking first at the case of molecules containing 3 atoms, two groups of triatomic molecule may be distinguished, that is linear and non-linear. Two simple examples of linear and non-linear triatomic molecule are represented by CO2 and water respectively. And here is the table where we show type of degree of freedom in case of linear and non-linear. And in case of transitional degree of freedom, in the case of linear and non-linear, that is 3. And in rotational degree of freedom, in the case of linear, that is 2. And in the case of non-linear, that is 3. Vibrational degree of freedom, in the case of linear, that is 3n minus 5, but 3n minus 6 in the case of non-linear. And the total degree of freedom, again linear as well as non-linear, is 3n. Here is the example of CO2, which is linear, and 3n minus 5, that is 9 minus 5, 4, and the 4 vibrational degree of freedom. And these are A, B, C, and D, 4 degree of vibrational motions. And A is not IR active because it is symmetric. B, C, and D are IR active because in these cases some dipole moment will be changed, and it is possible its positive and negative electrical centers are no longer coincident. A dipole moment is temporarily induced. IR electromagnetic radiation is just less energetic than visible light. This energy is sufficient to cause excitation of vibrational energy level, and the wave number, that is 1 upon lambda, in the case of IR 600 to 4000 per centimeter. Hooke's law can be applied to the vibrations of a covalent bond. Here is the wave number equal to 1 upon 2 pi c under root k upon mu. Here is the c's speed of light in per centimeter per second. And here K is the force constant in dynes per centimeter, a measure of bond strength. The stronger the bond, the larger the K, and mu is the induced mass in gram per atom. And here is the mu equal to M1 M2 upon M1 plus M2, and these two masses, atom 1 and atom 2, M1 and M2 in gram. Calculation of molecular vibration, for example, the stretching frequency per centimeter of CH can be calculated. In case of CH, the force constant K is 5 into 10 to the power 5 into 10 to the power 5 dynes per centimeter. And M1, again, that is in case of carbon, 12 divided by Avogadro number, and it equal to 1.99 into 10 to the power minus 23 gram. And in case of M2, hydrogen, atomic mass 1 divided by again Avogadro number, and we get in grams. And C is the speed of light, that is 3 into 10 to the power 10 centimeter per second. And when we put all these value in the formula and the wave number, we get that is 3023 per centimeter. And the observed value of CH bonds are in the region, that is 3320 to 2700 per centimeter, which differ from the calculated value, as the calculation does not take into account the environment of the CH group within the molecule. And force constant in case of double bond and triple bond, we can put all these values. Here is the label denoted by vibrational quantum number. V represent the potential energy of the harmonic oscillator. The transition 0 to 1, here V0 to V1, 0 to 1 is fundamental transition, and here transition 0 to n number, n is greater than 1, 0 to 1, 0 to 2, 0 to 3, 0 to 4, all are overtone transitions. And the transition 1 to n minus n to 1 to n, and n is greater than 1 are called hot transition, you call it hot bands. The vibrational energy of a chemical bond is quantized and can have the value E vibrational equal to V plus half h nu, where V is the number of the vibrational label and can have the value 0, 1, 2, 3, and h is the Planck constant. Transition from the ground state, that is V0, to the state of V1, V0 to V1, V1 absorb light strongly and give rise to intense band called the fundamental band, and delta E vibrational equal to E vibrational V minus 1, V equal to 1 minus E vibrational V equal to 0. And when we put all these value equal to 1 plus half h nu minus 0 plus half h nu, and it is around h nu. And the second excited state V2 with the absorption of IR radiation gives rise to weak band called overtone band, that is delta E vibrational equal to E vibrational V equal to 2 minus V E vibrational V equal to 0. And when we put all these value, and we get 2 h nu. It means in case of fundamental band, the overtone band is multiple of fundamental band, either double, triple, or etc. The value of stretching frequency of a bond increases with increasing the bond strength and decreasing the reduced mass of the bonded atom. The triple bond are stronger than the double bond, followed by the single bond between the same two atoms, and hence vibrational frequencies is in the order of C triple bond C is greater than C double bond C is greater than C single bond C. And CO again, C double bond O stretching will have higher frequency than C single bond O stretching respectively. And these are the value: C stretching at 1200 per centimeter, C double bond C stretching at 1640 per centimeter, and C triple bond C stretching at 2150 per centimeter. In case of C single bond O stretching at 1100 per centimeter, but in case of C double bond O stretching, it is around 1700 per centimeter. The vibrational frequency of a bond would increase with the decrease in reduced mass of the system. It implies that CH and OH stretching absorption should appear at higher frequency than CC and CO stretching frequency again, and CH stretching at 3000 per centimeter, and OH stretching is around 3600 per centimeter. Similarly, OH stretching should appear at higher frequency than OD stretching, and here is OH stretching around 3600 per centimeter, but in case of OD stretching, it is around 2600 per centimeter. The stretching of the spring require more energy than it bend it. The stretching absorption of a band always appear at higher energy than the bending absorption of the same band. The various stretching and bending modes can be represented by considering an AX2 group appearing as a portion of a molecule. For example, CH2 group in a hydrocarbon molecule, where we get these four type of stretching. And here is asymmetric molecular vibration, you call it. That is asymmetric stretching. It is around observed at 2926 per centimeter, and symmetric stretching it is observed around 2853 per centimeter, but bending vibrations, that is wagging, it is observed at 1350 to 1150 per centimeter, and twisting it is also observed at lower frequency here, 1350 to 1150 per centimeter. In addition to the fundamental vibrations, other frequency can be generated by modulation of fundamental bands. First, overtone band. Bands correspond to integral multiple of fundamental vibration. As we discussed earlier, the energy required for the first overtone is twice the fundamental, that is 2 h nu. Assuming evenly spaced energy levels, since the energy is proportional to the frequency absorbed, and this is proportional to the wave number, and they are very weak band. Other bands also recorded, that these are combination band. Two vibrational frequencies in a molecule coupled to give a new frequency within the molecule. This band is sum of the two interacting bands, and it is also a very weak band. And next is difference band. Similar to combination band, the observed frequency is the difference between the two interacting frequencies. And next is Fermi resonance band, when an overtone or a combination band has the same frequency as or a similar frequency to a fundamental. Two bands appear split either side of the expected value and are of about equal intensity. The coupled vibration is called a Fermi resonance, and the Fermi resonance effect usually lead to two bands appear close together when only one is expected, and the effect is greatest when the frequency match, but it is also present when there is a mismatch of the few tens of wave number. The two bands are referred to as a Fermi doublets. Thank you very much, and we will discuss interpretation part in my next video. Thank you.